Hello, welcome students. I am Rekha Thorat, Associate Professor. Today we will see some theorems on the topic sequences. Theorem number 5 is, statement of theorem is, if the sequence of real numbers, sequence Sn n going from 1 to infinity is convergent, then sequence Sn n going from 1 to infinity is bounded. Or the statement can be written in another format: every convergent sequence is bounded. Let us consider the proof of this theorem. Given sequence Sn n going from 1 to infinity is convergent sequence. Hence, limit of Sn as n tends to infinity equal to L. Hence, by definition of limit, given epsilon greater than 0, there exists another positive number n belongs to I such that modulus of Sn minus L is less than epsilon. Hence, modulus of Sn minus L is less than 1 for n is greater than or equal to n. Consider modulus of Sn. This can be written as modulus of L plus Sn minus L. Hence, modulus of Sn is less than or equal to modulus of L plus modulus of Sn minus L. Hence, modulus of Sn is less than or equal to L plus modulus of Sn minus L is less than 1. So that modulus of Sn is less than or equal to L plus 1 for n is greater than or equal to n. Let m equal to maximum of modulus of S in bracket modulus of S1 comma modulus of S2 comma modulus of S3 comma dash 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 modulus of Sn minus 1 bracket complete. Then we have modulus of Sn is less than m plus L plus 1. This proves that the sequence Sn n going from 1 to infinity is bounded, since modulus of Sn is less than m plus L plus 1 or n belongs to I. The sequence Sn is bounded. Now we consider monotonic sequence. Let us consider the definition of monotonic sequence. Let sequence Sn n going from 1 to infinity be a sequence of real numbers. If S1 is less than or equal to S2, less than or equal to S3, less than or equal to dash dash dash, less than or equal to Sn, less than or equal to Sn plus 1, less than or equal to dash dash dash, then the sequence Sn n going from 1 to infinity is called non-decreasing sequence. Non-decreasing, that means increasing, terms are increasing. If S1 is greater than or equal to S2, is greater than or equal to S3, is greater than or equal to dash dash dash, is greater than or equal to Sn, is greater than or equal to Sn plus 1, is greater than or equal to dash dash dash, then sequence Sn n going from 1 to infinity is called non-increasing sequence. That means this sequence is decreasing sequence. A sequence is called monotone sequence if it is either non-decreasing or non-increasing sequence or both. For example, sequence Sn n going from 1 to infinity equal to sequence 2, 4, 6, 8, 10 dash dash dash, 2, 4, 6, 8, 10, dash dash dash, 2n, dash dash dash, bracket complete. This is non-decreasing sequence, that means terms are increasing. Next example is sequence Sn n going from 1 to infinity equal to sequence 1, 2, 2, comma 3, comma 3, comma 4, comma 4, comma 4, comma dash dash dash, bracket complete. This is also non-decreasing sequence since terms are increasing. Consider next example, sequence Sn, n going from 1 to infinity equal to sequence 1 upon n, n going from 1 to infinity. This sequence is non-increasing sequence since the terms are decreasing. Since here terms are 1, 1/2, 1/3, sequence terms are goes on decreasing, that is non-increasing sequence. Next example is sequence Sn, n going from 1 to infinity equal to sequence 1, n going from 1 to infinity. It is both non-decreasing and non-increasing. This is a constant sequence. All these examples are monotonic examples of monotone sequences. Now consider note 1. Every non-decreasing sequence is bounded below. Every non-decreasing means increasing sequence is always bounded below. That means every non-decreasing sequence is bounded below. Non-decreasing means increasing sequence is always bounded below. Second note is every non-increasing sequence is bounded above. Non-increasing means decreasing sequence is bounded above. Now we consider one theorem. Statement of this theorem is a non-decreasing sequence which is bounded above is convergent. A non-decreasing means increasing sequence which is bounded above is convergent. It is considered the proof of this theorem. Suppose sequence Sn, n going from 1 to infinity is non-decreasing and bounded above sequence. Then the set A equal to sequence S1, S2, S3, dash dash dash, bracket complete is non-empty subset of R which is bounded above. Therefore, the set A has least upper bound, say M equal to least upper bound of S1 sequence S1, set S1, S2, S3, dash dash dash, bracket complete. Hence M equal to least upper bound for A. For given epsilon greater than 0, M minus epsilon is not upper bound of A, since M is an upper bound. Therefore, for some n belongs to I, Sn is greater than M minus epsilon. But since sequence Sn, n going from 1 to infinity, is non-decreasing, given sequence is non-decreasing, this implies Sn is greater than M minus epsilon for n greater than or equal to capital N. Denote this as number 1. On the other hand, since M is least upper bound for A, Sn is less than or equal to M. This implies Sn is less than M plus epsilon for n belongs to R. Denote this as number 2. From 1 and 2 we get M minus epsilon is less than Sn is less than M plus epsilon. This implies minus epsilon is less than modulus of Sn minus M is less than epsilon. And that means this implies modulus of Sn minus M is less than epsilon for n greater than or equal to capital N. This proves that limit of Sn as n tends to infinity equal to M. That means sequence Sn n going from 1 to infinity is convergent. It converges to m. Now we consider next theorem. Statement of this theorem is a non-increasing sequence, non-increasing means decreasing, which is bounded below is convergent. That means we have to prove that a non-decreasing sequence which is bounded below is convergent. Let us consider the proof of this theorem. Suppose sequence Sn n going from 1 to infinity is non-increasing and bounded below sequence. Then the set A equal to set S1, S2, S3, dash 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 is non-empty subset of R, which is also bounded below. Therefore, the set A has greatest lower bound. Let L equal to greatest lower bound of set S1, S2, S3, dash 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 bracket complete. Hence L equal to greatest lower bound for A. Hence for given epsilon greater than 0, m plus epsilon is not lower bound of for A. Therefore, for some n belongs to I, Sn is less than L plus epsilon. But sequence Sn n going from 1 to infinity is non-decreasing. This implies Sn is less than L plus epsilon for n greater than or equal to capital N. Give this as number 1. On the other hand, since L is least upper bound for the set S1, S2, S3 dash dash dash, Sn is greater than or equal to capital L. This implies Sn is greater than L minus epsilon for n belongs to I. Denote it as number 2. From 1 and 2 we get L minus epsilon is less than Sn is less than L plus epsilon. This implies minus epsilon is less than modulus of Sn minus L is less than epsilon. That means this is by definition, this implies modulus of Sn minus L is less than epsilon or n greater than or equal to capital N. Hence, limit of Sn as n tends to infinity equal to L. Hence, sequence Sn n going from 1 to infinity is convergent. Thus, we have proved that a non-decreasing sequence, non-decreasing means increasing sequence, which is bounded below is convergent. It means decreasing sequence which is bounded below is convergent. Here we have taken that limit of Sn as n tends to infinity equal to L, since by definition of limit modulus of Sn minus L is less than epsilon, it is L minus epsilon less than Sn less than L plus epsilon means modulus of Sn minus L is less than epsilon for n greater than or equal to capital N. This is by definition of limit. Hence, limit of Sn as n tends to infinity equal to L. Hence, limit of this sequence is L. That means sequence Sn n going from 1 to infinity is convergent sequence. Thus we have proved this theorem. Thank you.